Plot the ordered triple (-1, 2, -2) in space. Plot the ordered triple 3, -1, -1 in space. Plot the ordered triple -1, -2, -1 in space. Plot the ordered triple -3, -2, 1 in space. Find the distance between the ordered triple 0, 1, 3 and the ordered triple 1, 4, -2. Begin by writing the distance formula in space. Substitute the ordered triple 1, 4, -2 as x sub 2, y sub 2, and z sub 2, and substitute the ordered triple 0, 1, 3 for x sub 1, y sub 1, and z sub 1. This simplifies to the square root of the quantity 1 plus 9 plus 25, which equals the square root of 35. So the distance between the ordered triple 0, 1, 3 and the ordered triple 1, 4, -2 is the square root of 35. Find the midpoint of the line segment joining the ordered triple 7, -1, -2 and the ordered triple 3, -5, 4. Begin by writing the formula for the midpoint. Then substitute the ordered triple 7, -1, -2 for x sub 1, y sub 1, and z sub 1, and substitute the ordered triple 3, -5, 4 for x sub 2, y sub 2, and z sub 2. This simplifies to the ordered triple 5, -3, 1. So the midpoint of the line segment joining the ordered triples 7, -1, -2, and 3, -5, 4 is the ordered triple 5, -3, 1. Find the standard equation of the sphere with the center, the ordered triple 1, 3, 2, and radius 4. Begin by writing the standard equation of a sphere. The quantity x minus h squared plus the quantity y minus k squared plus the quantity z minus j squared equals r squared. Then substitute 1 for h, 3 for k, 2 for j, and 4 for r. The standard equation of the sphere is the quantity x minus 1 squared plus the quantity y minus 3 squared plus the quantity z minus 2 squared equals 4 squared. Find the center and radius of the sphere x squared plus y squared plus z squared plus 6x minus 4y plus 8z minus 7 is equal to 0. To obtain the standard equation of this sphere, complete the square as follows. Add 7 to both sides and group terms with the same variable. To complete the square with the x terms, take half of 6, which is 3, and square that, which is 9, and add that to both sides. To complete the square with the y terms, take half of 4, which is 2, and square that, which is 4, and add that to both sides. To complete the square with the z terms, take half of 8, which is 4, and square that, which is 16, and add that to both sides. Next, simplify the equation. So the center of the sphere is the ordered triple -3, 2, -4, and its radius is 6. Sketch the xz trace of the sphere. The quantity x minus 1 squared plus the quantity y minus 3 squared plus the quantity z minus 8 squared is equal to 10 squared. To find the xz trace of this surface, use the fact that every point in the xz plane has a y-coordinate of 0. By substituting y equals 0 into the original equation, the resulting equation will represent the intersection of the surface with the xz plane. First, write the original equation, substitute 0 for y, simplify, subtract 9 from both sides, rewrite 91 as the square root of 91 squared to form the equation of the circle. You can see that the xz trace is a circle in the xz plane with center the ordered pair 1, 8 and having radius the square root of 91. Find the component form and magnitude of the vector v having initial point the ordered triple 1, -4, 3, and terminal point the ordered triple 2, 2, -1. Then find a unit vector in the direction of v. The component form of v is 2 minus 1, 2 minus -4, and -1 minus 3, which equals 1, 6, -4. This implies that the magnitude of v is the square root of the quantity 1 squared plus 6 squared plus -4 squared, which is equal to the square root of the quantity 1 plus 36 plus 16, which is equal to the square root of 53. A unit vector in the direction of v is v divided by the magnitude of v, which is equal to 1 divided by the square root of 53 times the vector 1, 6, -4, which is equal to the vector 1 divided by square root of 53, 6 divided by square root of 53, and -4 divided by square root of 53. And this simplifies to the vector the square root of 53 divided by 53, 6 times the square root of 53 divided by 53, and -4 times the square root of 53 divided by 53. Find the dot product of the vector 4, 0, 1 and the vector -1, 3, 2. The dot product of the vector 4, 0, 1 and the vector -1, 3, 2 is equal to 4 times -1 plus 0 times 3 plus 1 times 2, which equals -4 plus 0 plus 2, which is equal to -2. Find the angle between u equals the vector 1, -2, 4, and v equals the vector 2, -3, -1. To find the angle between two vectors u and v, use the formula cosine of theta is equal to the dot product of the vectors u and v divided by the product of the magnitudes of the vectors u and v. Substitute the corresponding values, so cosine of theta is equal to the quantity 1 times 2 plus -2 times -3 plus 4 times -1 divided by the quantity, the magnitude of the vector 1, -2, 4 times the magnitude of the vector 2, -3, -1, which is equal to the quantity 2 plus 6 minus 4 divided by the quantity, the square root of the quantity 1 squared plus -2 squared plus 4 squared times the square root of the quantity 2 squared plus -3 squared plus -1 squared, which is equal to 4 divided by the quantity, the square root of 21 times the square root of 14, which is equal to 4 divided by the square root of 294, which simplifies to 4 divided by the quantity 7 times the square root of 6. This implies that theta is equal to arc cosine of the quantity 4 divided by the quantity 7 times the square root of 6, which is approximately 76.5 degrees. Vector w has initial point the ordered triple 2, -2, 1, and terminal point 0, 4, -3. Which of the following vectors is parallel to w? Begin by writing w in component form. W equals the vector -2, 6, -4. For part A, the vector u equals -1, 3, -2 is equal to 1/2 times the vector -2, 6, -4, which is equal to 1/2 w. From this, you can conclude that u and w are parallel. For part B, there does not exist any scalar c such that the vector -2, 6, -5 equals c times the vector -2, 6, -4. So you can conclude that v and w are not parallel. For part Z, the vector 3, -9, 6 is equal to -3/2 times the vector -2, 6, -4, which equals -3/2 w. So you can conclude that z and w are parallel. Determine whether the points p, the ordered triple, -2, 7, -3, q, the ordered triple, 1, 4, 3, and r, the ordered triple, 3, 2, 7, are collinear. The component forms of the vectors pq and pr are: the vector pq is equal to 1 minus -2, 4 minus 7, and 3 minus -3, which is equal to the vector 3, -3, 6. And the vector pr is equal to the vector 3 minus -2, 2 minus 7, and 7 minus -3, which is equal to the vector 5, -5, 10. Because the vector pq is equal to 3/5 times the vector pr, you can conclude that they are parallel. Therefore the points p, q, and r lie on the same line as shown. The initial point of the vector v equals 2, -3, 6 is p, the ordered triple, 1, -2, -5. What is the terminal point of this vector? Using the component form of the vector whose initial point is p, the ordered triple, 1, -2, -5, and whose terminal point is q, the ordered triple, q sub 1, q sub 2, and q sub 3, you can write the vector pq equals the vector q sub 1 minus p sub 1, q sub 2 minus p sub 2, and q sub 3 minus p sub 3. Then substitute 1 for p sub 1, -2 for p sub 2, and -5 for p sub 3. And this equals the vector 2, -3, 6. This implies that q sub 1 minus 1 equals 2, q sub 2 plus 2 equals -3, and q sub 3 plus 5 equals 6. So the solutions of these equations are q sub 1 equals 3, q sub 2 equals -5, and q sub 3 equals 1. So the terminal point is q, the ordered triple, 3, -5, 1. A weight of 240 pounds located at S, the ordered triple, 0, 3, -2, is supported by ropes tied to the points p, the ordered triple, 3, 0, 0, q, the ordered triple, 0, 6, 0, and r, the ordered triple, -3, 0, 0. Find the force or tension on each rope. The downward force of the weight is represented by the vector W equals the vector 0, 0, -240. The force vectors corresponding to the ropes are as follows. U is equal to the magnitude of U times the vector SP divided by the magnitude of the vector SP, which is equal to the magnitude of U times the vector 3 minus 0, 0 minus 3, and 0 minus -2, divided by the square root of the quantity 3 squared plus -3 squared plus 2 squared. V is equal to the magnitude of V times the vector SQ divided by the magnitude of the vector SQ, which is equal to the magnitude of V times the vector 0 minus 0, 6 minus 3, and 0 minus -2, divided by the square root of the quantity 0 squared plus 3 squared plus 2 squared, which is equal to the magnitude of V times the vector 0, 3, 2, divided by the square root of 13. Z is equal to the magnitude of Z times the vector SR divided by the magnitude of the vector SR, which is equal to the magnitude of Z times the vector -3 minus 0, 0 minus 3, and 0 minus -2, divided by the square root of the quantity -3 squared plus -3 squared plus 2 squared, which is equal to the magnitude of Z times the vector -3, -3, 2, divided by the square root of 22. For the system to be in equilibrium, it must be true that U plus V plus Z plus W is equal to 0, or U plus V plus Z is equal to -W. This yields the following system of linear equations. 3 divided by the square root of 22 times the magnitude of U plus -3 divided by the square root of 22 times the magnitude of Z is equal to 0. -3 divided by the square root of 22 times the magnitude of U plus 3 divided by the square root of 13 times the magnitude of V minus 3 divided by the square root of 22 times the magnitude of Z is equal to 0, and 2 divided by the square root of 22 times the magnitude of U plus 2 divided by the square root of 13 times the magnitude of e plus 2 divided by the square root of 22 times the magnitude of z is equal to 240. This system has the solution: the magnitude of u is approximately 140.7, the magnitude of e is approximately 216.3, and the magnitude of z is approximately 140.7. So the rope attached at point P has about 140.7 pounds of tension, the rope attached at point Q has about 216.3 pounds of tension, and the rope attached at point R has about 140.7 pounds of tension. Given U is equal to I minus 3J plus 2K and V is equal to 2I minus J plus 2K, find each cross product. The cross product of U and V is equal to the determinant form IJK 1, 3, negative 2 and 2, negative 1, 2, which is equal to the cofactor expansion of the determinant form negative 3, 2, negative 1, 2 times I minus the determinant form 1, 2, 2, 2 times j plus the determinant form 1, negative 3, 2, negative 1 times k, which is equal to the quantity negative 6 plus 2i minus the quantity 2 minus 4j plus the quantity negative 1 plus 6k, which is equal to negative 4i plus 2j plus 5k. The cross product of V and U is equal to the determinant form of IJK 2, negative 1, 2 and 1, negative 3, 2, which is equal to the cofactor expansion, the determinant form negative 1, 2, negative 3, 2 times I minus the determinant form of 2, 2, 1, 2 times j plus the determinant form of 2, negative 1, 1, negative 3 times k, which is equal to the quantity negative 2 plus 6 times I minus the quantity 4 minus 2 times j plus the quantity negative 6 plus 1 k, which is equal to 4i minus 2j minus 5k. The cross product of V and V is equal to the determinant form IJK 2, negative 1, 2 and 2, negative 1, 2, which is equal to the cofactor expansion of the determinant form negative 1, 2, negative 1, 2 times I minus the determinant form of 2, 2, 2, 2 times j plus the determinant form of 2, negative 1, 2, negative 1 times k, which is equal to the quantity negative 2 plus 2 times I minus the quantity 4 minus 4 times j plus the quantity negative 2 plus 2 times k, which is equal to 0. Find a unit vector that is orthogonal to both u is equal to 2i plus 4j minus 3k and v is equal to negative 2i minus 3j plus 2k. The cross product of u and v is orthogonal to both u and v. The cross product of u and v is equal to the determinant form of ijk 2, 4, negative 3 and negative 2, negative 3, 2, which is equal to the cofactor expansion of the determinant form 4, negative 3, negative 3, 2 times I minus the determinant form 2, negative 3, negative 2, 2 times j plus the determinant form of 2, 4, negative 2, negative 3 times k, which is equal to the quantity 8 minus 9 times I minus the quantity 4 minus 6 times j plus the quantity negative 6 plus 8 times k, which is equal to negative I plus 2j plus 2k. Because the magnitude of the cross product of u and v is equal to the square root of the quantity 1 squared plus 2 squared plus 2 squared, which is equal to the square root of the quantity 1 plus 4 plus 4, which simplifies to 3, a unit vector orthogonal to both u and v is the cross product of u and v divided by the magnitude of the cross product of u and v, which is equal to 1/3 times the quantity negative I plus 2j plus 2k, which is equal to negative 1/3 I plus 2/3 j plus 2/3 k. Show that the quadrilateral with the following vertices is a parallelogram. Then find the area of the parallelogram. Using the points A, B, C, and D, you can find the vectors. The vector AB is equal to 3 minus 4, 4 minus 3, and 2 minus 0, which is equal to negative I plus j plus 2k. The vector AD is equal to the vector 4 minus 4, 1 minus 3, and 4 minus 0, which is equal to negative 2j plus 4k. The vector CD is equal to the vector 4 minus 3, 1 minus 2, and 4 minus 6, which is equal to I minus j minus 2k. The vector CB is equal to the vector 3 minus 3, 4 minus 2, and 2 minus 6, which is equal to 2j minus 4k. Because the vector AB is equal to the opposite of the vector CD, and the vector AD is equal to the opposite of the vector CB, you can conclude that the vector AB is parallel to the vector CD, and the vector AD is parallel to the vector CB. So it follows that the quadrilateral is a parallelogram with the vector AB and the vector AD as adjacent sides. Moreover, because the cross product of the vector AB and the vector AD is equal to the determinant form ijk, negative 1, 1, 2, and 0, negative 2, 4, which is equal to the cofactor expansion of the determinant form 1, 2, negative 2, 4 times I minus the determinant form of negative 1, 2, 0, 4 times j plus the determinant form of negative 1, 1, 0, negative 2 times k, which is equal to the quantity 4 plus 4 times I minus the quantity negative 4 minus 0 j plus the quantity 2 minus 0 k, which is equal to 8I plus 4j plus 2k. The area of the parallelogram is the magnitude of the cross product of the vector AB and the vector AD, which is equal to the square root of the quantity 8 squared plus 4 squared plus 2 squared, which is equal to the square root of 84, which simplifies to 2 times the square root of 21, which is approximately 9.17 square units. Find the area of the triangle with vertices A, the order triple, 3, 2, 1, B, the order triple, 3, 1, 7, and C, the order triple, 5, 2, 6. First, find the vectors AB and AC. AB equals the vector negative j plus 6k, and AC equals the vector 2I plus 5k. The cross product of the vector AB and AC is the determinant I, j, k, 0, negative 1, 6, 2, 0, 5, which equals the determinant negative 1, 6, 0, 5 times I, minus the determinant 0, 6, 2, 5 times j, plus the determinant 0, negative 1, 2, 0 times k, which equals the quantity negative 5 minus 0I, minus the quantity 0 minus 12j, plus the quantity 0 plus 2k, which equals negative 5I plus 12j plus 2k. So the area of the triangle is 1/2 times the magnitude of the cross product of the vectors AB and AC, which equals 1/2 times the square root of the quantity negative 5 squared plus 12 squared plus 2 squared, which equals 1/2 times the square root of the quantity 25 plus 144 plus 4, which equals 1/2 times the square root of 173, which is approximately 6.58 square units. So the area of the triangle is approximately 6.58 square units. Find the volume of the parallelepiped having u is equal to 2I minus j plus 4k, v is equal to I plus 3j minus 2k, and w is equal to 2I minus 2j plus 3k as adjacent sides. The value of the triple scale product is as follows. The dot product of u and the cross product of v and w is equal to the determinant form 2, negative 1, 4, 1, 3, negative 2, and 2, negative 2, 3, which is equal to the cofactor expansion 2 times the determinant form 3, negative 2, negative 2, 3, minus negative 1 times the determinant form 1, negative 2, 2, 3, plus 4 times the determinant form 1, 3, 2, negative 2, which is equal to 2 times the quantity 9 minus 4, plus the quantity 3 plus 4, plus 4 times the quantity negative 2 minus 6, which is equal to 2 times 5 plus 7 plus 4 times negative 8, which is equal to 10 plus 7 minus 32, which equals negative 15. So the volume of the parallelepiped is equal to the absolute value of the triple scalar product, which is equal to the absolute value of negative 15, which is equal to 15 cubic units. Find parametric and symmetric equations of the line L that passes through the point the order triple 2, 1, negative 3, and is parallel to V, the vector 4, negative 2, 7. To find a set of parametric equations of the line, use the coordinates x sub 1 is equal to 2, y sub 1 is equal to 1, and z sub 1 is equal to negative 3, and direction numbers a is equal to 4, b is equal to negative 2, and c is equal to 7. The set of parametric equations is x is equal to 2 plus 4t, y is equal to 1 minus 2t, and z is equal to negative 3 plus 7t. Because a, b, and c are all non-zero, a set of symmetric equations is the quantity x minus 2 divided by 4 is equal to the quantity y minus 1 divided by negative 2 is equal to the quantity 7 plus 3 divided by 7. Find parametric and symmetric equations of the line that passes through the points the order triple 1, negative 6, 3, and the order triple 3, 5, 8. Begin by letting P equal the order triple 1, negative 6, 3, and Q equal the order triple 3, 5, 8. Then a direction vector for the line passing through P and Q is V is equal to the vector PQ, which equals the vector 3 minus 1, 5 minus negative 6, and 8 minus 3, which equals the vector 2, 11, 5, which is equal to the vector A, B, C. Using the direction numbers with the initial point P, the order triple 1, negative 6, 3, you can obtain the parametric equations x is equal to 1 plus 2t, y is equal to negative 6 plus 11t, and z is equal to 3 plus 5t. Because a, b, and c are all non-zero, a set of symmetric equations is the quantity x minus 1 divided by 2 is equal to the quantity y plus 6 divided by 11 is equal to the quantity z minus 3 divided by 5. Find the general form of the equation of the plane passing through the point the order triple negative 2, 1, 3, and perpendicular to the vector n is equal to 2i minus j plus 6k. Using the direction numbers for n is equal to 2i minus j plus 6k and the initial point, the order triple x sub 1, y sub 1, z sub 1 is equal to the order triple negative 2, 1, 3, you can determine an equation of the plane to be as follows. A times the quantity x minus x sub 1 plus b times the quantity y minus y sub 1 plus c times the quantity z minus z sub 1 is equal to 0. Substitute the corresponding values for a, b, c, and x sub 1, y sub 1, and z sub 1. Expand the left side of the equation to get 2x plus 4 minus y plus 1 plus 6z minus 18 is equal to 0. Simplify the left side of the equation to get 2x minus y plus 6z minus 13 is equal to 0. Find the general form of the equation of the plane passing through the points the order triple 1, 0, 5, the order triple negative 1, negative 2, 9, and the order triple 2, 3, 2. To find the equation of the plane, you need a point in the plane and a vector that is normal to the plane. There are three choices for the point, but no normal vector is given. To obtain a normal vector, use the cross product of vectors u and v, extending from the point, the order triple 1, 0, 5, to the points, the order triple -1, -2, 9, and the order triple 2, 3, 2, respectively, as shown. The component forms of u and v are as follows. U is equal to the vector -1 minus 1, -2 minus 0, and 9 minus 5, which equals the vector -2, -2, 4. And v is equal to the vector 2 minus 1, 3 minus 0, and 2 minus 5, which equals the vector 1, 3, -3. Then the cross product of u and v is equal to the determinant form I, j, k, -2, -2, 4, and 1, 3, -3, which is equal to -6i minus 2j minus 4k, which is equal to the vector a, b, c. So a is equal to -6, b is equal to -2, and c is equal to -4 is normal to the given plane. Using these direction numbers for n and the initial point, the order triple x sub 1, y sub 1, z sub 1 is equal to the order triple 1, 0, 5, you can determine an equation of the plane to be as follows. A times the quantity x minus x sub 1 plus b times the quantity y minus y sub 1 plus c times the quantity z minus z sub 1 is equal to 0. Substitute the corresponding values for x sub 1, y sub 1, z sub 1, and a, b, c. Expand the left side of the equation to get -6x plus 6 minus 2y minus 4z plus 20 equals 0. Combine like terms to get -6x minus 2y minus 4z plus 26 is equal to 0. Multiply both sides by -1 to get 6x plus 2y plus 4z minus 26 is equal to 0. Find the angle between the two planes given by 2x plus y plus 3z is equal to 0 and 4x minus 2y minus 2z is equal to 0, and find parametric equations of the line of intersection. The normal vectors for the planes are n sub 1 is equal to the vector 2, 1, 3, and n sub 2 is equal to the vector 4, -2, -2. The angle between the two planes is determined as follows. Cosine of theta is equal to the absolute value of the dot product of n sub 1 and n sub 2 divided by the quantity, the magnitude of n sub 1 times the magnitude of n sub 2, which is equal to the absolute value of the quantity 2 times 4 plus 1 times -2 plus 3 times -2 divided by the quantity, the square root of the quantity 2 squared plus 1 squared plus 3 squared times the square root of the quantity 4 squared plus -2 squared plus -2 squared, which is equal to the absolute value of 0 divided by the quantity, the square root of 14 times the square root of 24, which is equal to 0. This implies that the angle between the two planes is theta is equal to pi divided by 2 radians, or 90 degrees, as shown. You can find the line of intersection of the two planes by simultaneously solving the two linear equations representing the planes. Multiply the first equation by 2 and leave the second equation alone. Add the two equations to get 8x plus 4z is equal to 0. This implies that x is equal to 1/2 z. Substituting x is equal to 1/2 z back into one of the original equations, you can determine y. Simplify the equation and solve for y, which is equal to -4z. Finally, by letting t equal 1/2 z, you obtain the parametric equations. X equals t equals x sub 1 plus at. Y equals -8t equals y sub 1 plus bt. Z equals 2t equals z sub 1 plus ct. Because the order triple x sub 1, y sub 1, z sub 1 equals the order triple 0, 0, 0 lies in both planes, you can substitute for x sub 1, y sub 1, and z sub 1 in these parametric equations, which indicates that a equals 1, b equals -8, and c equals 2 are the direction numbers for the line of intersection. Find the distance between the point Q, the ordered triple, -6, 2, 1, and the plane 2x plus 5y minus z equals 3. You know that n is equal to the vector 2, 5, -1 is normal to the plane 2x plus 5y minus z equals 3. To find a point in the plane, let x equals 0 and y equals 0, and obtain the point P, the ordered triple, 0, 0, -3. The vector from P to Q is -6 minus 0, 2 minus 0, and 1 minus -3, which is equal to the vector -6, 2, 4. The formula for the distance between a point and a plane produces the following. The distance is equal to the absolute value of the dot product of the vector PQ and n divided by the magnitude of n, which is equal to the absolute value of the dot product of the vector -6, 2, 4, and the vector 2, 5, -1, divided by the square root of the quantity 2 squared plus 5 squared plus -1 squared, which is equal to the absolute value of the quantity -6 times 2 plus 2 times 5 plus 4 times -1, divided by the square root of the quantity 4 plus 25 plus 1, which is equal to the absolute value of -6 divided by the square root of 30, which is equal to 6 divided by the square root of 30.